which I hadn't heard of before, but apparently it's somewhere between a half an hour and an hour, probably depending on traffic, north of Philly. As a result of that, I have seen more Philadelphia Flyer and Eagles and Phillies jerseys in my office than I had over my 15 years here so far. But anyway, those poor life choices aside, she did make the excellent choice to switch from the professional masters, which she originally came here to do in 2023, but when she realized that she really loved research, switched into the research master's program and decided she wanted to do some satellite remote sensing work with me. And so she's been working on the PREFIRE, the Polar Radiant Energy in the Far Infrared Experiment. I emphasize the word polar. With me to study tropical convection, of course, because why not? No, this is the beauty of our satellite missions. They measure all around the world all the time, and so we think, and hopefully she'll be able to convince you that there's some good information in the far infrared about tropical anvil clouds. And I think with that, I will hand it off to Carolyn.
Cool, okay. Is this still working?
It's working.
Okay, cool. So, thank you. I personally don't think my sports opinions are bad life choices, but that's fine. So today I'll be talking about a qualitative far infrared characterization of convective cloud tops. I don't have an official roadmap slide, but just as a quick outline, I'm going to do a pretty brief science introduction. I'll introduce you to PREFIRE, the mission that Tristan was talking about, and then we'll kind of get into what I've actually been doing for my master's thesis. So at a quick baseline, I wanted to set up just the very broad overview of what's underlying the motivation here, which is understanding that radiative energy balance of the Earth. So we have, at broad strokes, most of you will be familiar with, we have wavelengths of incoming radiation from the sun and wavelengths of outgoing radiation from the Earth. That incoming radiation is in the short wave, whereas the outgoing radiation is in the long wave, as you heard me almost say. So understanding kind of how this works and how we compensate for regional deficits in that incoming and outgoing radiation is really how we understand how our weather works, because that compensation is what drives large-scale climate in the Earth. So we want to really kind of characterize this whole spectrum and understand what's happening. We're mostly familiar with how incoming energy from the sun, a lot of people will have seen this kind of spectrum here, but that outgoing radiation that we also see is also along a kind of spectrum, and so characterizing that is one of the major pieces to understanding this radiative energy budget. So, there's a slide missing. Okay, well, I don't know where that slide went, but this is the same figure that was going to be on that slide, and I basically was going to talk about how we characterize the outgoing radiation of the Earth using the Planck function, which is a measure of the radiation that you would see from a perfectly emitting black body. So in the top, we see what that function would look like for a 14 degrees Celsius Earth surface. This green line here is just in the middle of this Earth emission, and then this bottom line is what it would look like for a negative 55 degrees Celsius tropopause. The most important thing to understand about this is this is entirely temperature dependent. So it can give us a lot of information about temperature that we can kind of apply to other things about the atmosphere itself. And then the Earth, because the Earth is not in fact a perfectly emitting black body, it is more accurately represented by these black lines here. And you can see some different kind of regions where we're either really strongly absorbing, like in this carbon dioxide band here, or where the atmosphere becomes almost perfectly transparent, and we can get a really accurate read of approximately what the Earth's surface would be. So we have a couple of window regions between 8 and 9.5 microns, between 10 and 12.5 microns, and what is so far unmeasured is this semi-transparent window between 18 and 25 microns. So between all three of those, they're responsible for the majority of Earth's emission. And so these two over here, which on my slide that is gone would have had nice little boxes showing you where they are. But that 8 and 10 one, they have both been measured quite extensively from a satellite and also ground-based perspective. But at least from the satellite perspective, we have not measured that 18 to 25 micron window band globally at all. This is a significant gap in our understanding of the outgoing long wave radiation because it's this region. We're going to call it the far infrared, and as you can see here, the contribution that the far infrared makes to that outgoing long wave radiation is quite significant. So this is just all of that outgoing long wave radiation, and then this is the estimated far infrared fraction. So what does the far infrared actually contribute to this? And you can see that at the poles especially, which is, as Tristan said, where PREFIRE is concentrated, the fraction of outgoing long wave radiation contributed by the far infrared is as high as 65% of what's actually being emitted. And in the region that I will be looking at, which is basically the upper mid-latitudes to the lower mid-latitudes, so everything outside of that, we can see that even though it's less of a contribution than at the poles, it's still a pretty significant portion. The end of this color bar is at 40%. So even at portions where it's below here, it's still, that's 40% of the emission is just not measured right now from a satellite perspective. And we've talked, I will go into, I'm just going to be talking about convection. And you can see that in the region where we see particularly intense convection, that fraction is actually a lot higher. So characterizing far infrared behavior at those regions is going to be a pretty significant contribution to understanding that long wave emission spectrum. So here's how we're going to kind of address that gap, is PREFIRE, which is the mission that Tristan talked about. It's the polar radiant energy in the far infrared experiment. It's two 6U CubeSats, so really, really small satellites in sun-synchronous polar orbits. Here it is. This is a picture from, is it whatever company built it, which I've forgotten the name of, but this is what's actually in space. The main instrument on board is called the thermal IR spectrometer, so that's what's actually measuring these like new science information. It is an ambient temperature far infrared spectral imager, so it's taking passive measurements. It has a resolution of 0.84 microns between 5 and 53 microns, so that gives us a total of 64 channels with which to measure pretty much the entire Planck spectrum, Planck function. Its swath is 250 kilometers across. It's comprised of 8 non-contiguous cross-track seams with a separation between them of about 24.2 kilometers and individual footprints of 11 by 30 kilometers. That's a really significant difference. And so I'm going to show you kind of what this looks like, just because this is kind of a little messy to conceptualize by yourself. But before I do that, I did want to address the products I'll be using from PREFIRE are going to be our level 1B radiances and brightness temperatures, which we do have at a global level. We have complete global coverage of the level 1B radiances and brightness temperatures. In the future, we hope to expand our level 2 products to also include full global coverage. But because I am kind of completely branched out from the polar focus of this mission, I get to more or less forge new ground with just our level 1B products, which is, I think, pretty exciting. So this is a PREFIRE granule. Just a quick overview. Here's pretty much one PREFIRE orbit. You'll see, you know, it's orbiting. This gap here is one of our downlinking centers. So when PREFIRE is passing over this center, we see a gap in science data where it's passing that information down. And we have another one of these downlinking centers in Spain, so that we, even though we have this gap here, we don't completely lose science data over this region. This is a regional view of this same granule in this area, just showing you those 8 cross-tracks I was talking about, those eight scenes that I was talking about. The separation, like I said here, is about 24 kilometers, and this is going to be about 250 kilometers apart. And you can see this small gap here is just for sensor calibration. So these are pretty consistent, and you'll see them in a couple of the actual cases that we look at. So moving on to kind of what am I actually trying to investigate? So what can the far infrared spectra actually tell us about the radiative effects of convection? What can the information that PREFIRE is giving us start to tell us about how convection in particular is affecting the radiative energy budget? Like Tristan said, I took this picture. You'll see this picture, I think, one more time just because I like it so much. The person next to me in the window seat probably thought I was a little crazy because I was just plastered to the screen taking pictures of this. But anyway, So to understand how the convection is actually going to impact the radiative energy budget, we want to talk about the radiative effects of clouds. So clouds are going to affect this budget by impacting both short and long wave radiation according to a number of different cloud properties. These are kind of all interwoven with each other. Like it's difficult to isolate one of these and say definitively, yes, this is the only source of this alteration. So I'm just going to go through them quickly, and we'll keep them in mind as we move through the rest of the presentation. So the height of the cloud is going to impact the background atmospheric composition that the cloud is actually located in. So that's going to impact how how extinction actually impacts the radiation kind of moving through the cloud. The habit of a cloud, so when I say habit of a cloud, I really mean the habit of the ice particles comprising the cloud. So that is going to have an impact on scattering and absorption properties of the cloud, but that impact is going to vary in the radiative sense depending on the height of the cloud. If a lower cloud, for example, versus a higher cloud is going to have more background, say, water vapor, which is going to impact how much the actual scattering difference between ice habits impacts the radiative effect of the cloud as a whole. Whereas higher, thinner clouds are going to kind of demonstrate this ice habit impact a lot more strongly because the background atmospheric composition is different. Particle size at a broad strokes, larger particles are going to depress upwelling radiance. So again, ice habit dependent, you're generally going to see less radiance making it through a cloud if the particles are larger. And then optical depth is the last one I'm going to talk about really quickly. Radiative effects are sensitive to the liquid water path in particularly optically thin clouds. So all of these are going to affect how a cloud signature presents in the Planck function. So with that information, what is the information we have already, that mid-IR spectra that we have measured? What has that taught us about cloud properties? So this is from a paper that was modeling a tropical atmosphere. So it's showing the impact of the change in measured brightness temperature based on changing wave number, changing optical depth, and changing particle size. So there's a lot of information contained on here. Optical depth is increasing this way. Wave number is on the x-axis, and on the top x-axis, I have translated this to wavelength because that makes more sense to me personally. So wavelength is increasing in this direction, and wave number is increasing in this direction. And these are different cloud particle sizes. So your largest particle is always going to be at the kind of bottom of all of these figures. And there's two primary signals that I want to kind of point out that we're going to apply later. So the first is that you'll notice in this window band right here, this 10 to 12.5 micron, the brightness temperature varies really, really strongly between, say, around 10 and 12. Like the difference there is incredibly large the difference is significant with regard to wavelength. And the other thing I wanted to point out is that the different particle sizes themselves are going to show variations like between themselves. So you see this big gap in the brightness temperature registered by a smaller particle versus a larger particle. And you also see not only this gap, but the steepness of this slope here is getting smaller as optical depth increases. So we're going to keep both of those things in mind when we look at the split window method, which is a method that was first proposed in 1985, which I think tells you a lot given that it is still in use today, that uses that brightness temperature difference that I mentioned between two window IR wavelengths to infer information about cloud optical thickness and effective particle size. So this is a really, really pretty kind of model of what this might look like from a paper written by Yang et al. In 2015. So we have brightness temperatures, 12 micron on the x-axis, and the difference on the y-axis between 11 and 12 microns. And you can see we're forming some isolines here of particle size. So these arcs are different particle sizes. And these dashed lines are isolines of optical depth. And so with that information, you can kind of determine information about both of those aspects of a cloud. And the two things I want to point out here is at points where optical depth is very large or where it is very small, you can see those arcs kind of pointing, pinching. So the information that you can gain here and here is a lot less than the information you can have here. We kind of get that to a point where the radiances become saturated and your information becomes essentially minimal here. And you'll also see, as particles get larger, the differences between the isoline brightness temperature differences become a lot smaller, and in some cases maybe within the margin of error for whatever instrument you're using. So that being said, can the FIR contribute to kind of solving any of those kind of deficiencies? So the FIR can basically provide refined information about a lot of the different things that I talked about previously. So with habit, it's less strongly, it is proposed, I should say, that it is less strongly impacted by habit size due to the relative size of the particles to the wavelength. For particle size, these are both, the particle size and optical depth are both propositions that I'll go into in more detail later, but it is basically suggested that for optically thick clouds, some FIR wave number brightness temperature differences can distinguish between particle sizes more effectively than in the mid-IR. And for optical depth, the same thing, but with distinguishing differences in optical depth for optically thin clouds. And then the last thing that I wanted to talk about with regards to this is that the FIR is really, really good at isolating high clouds because it's very, very good at cold, dry clouds, because a really significant aspect of the far infrared is that it is super strong in water vapor absorption, which is kind of a double-edged sword, right? So you don't get a lot of information about tropospheric processes, but you also don't get your information about high up processes corrupted by upwelling radiances from the lower atmosphere. It basically masks it out, and you can say, yes, what I'm seeing is this high cloud signature. So it's really good at kind of separating out those high clouds. And I wanted to talk a little bit more about that because I wanted to talk about why I'm looking, as opposed to in the Arctic, looking at the tropics. So like I said, this is the PREFIRE mission focus, and this is kind of where I'm looking. And these are simulated Arctic winter and tropical atmosphere transmittances from another group in Quebec that is also working in the far infrared. So transmittance is basically just measuring the radiation that survives along a given path. And you can see these red kind of warmer colors are between 70 and 90% transmittance. And all the way out into the 50 micron bands, which is about where PREFIRE stops, we can see that transmittance is incredibly usable, pretty much at the height of the tropical tropopause the whole way, as determined by this reanalysis analysis of the height of the cold point tropopause, and also that for mid-latitude cirrus, so convection in the mid-latitudes, it's useful to not as deep in, but really pretty far out. So we see this kind of slope here, which is also a much more kind of gentle slope than where you would see it in, say, these window bands or near these window bands. And so the difference in a cloud signature at 20 microns versus 50 microns can also, because of this transmittance difference, provide us information about the cloud top height. So all of that being said, these are a couple of the questions that I'll be looking at in the actual science part of this presentation. So the first one is just, can PREFIRE actually successfully identify convective ice clouds? And then these second two I'll be kind of looking at together. So wondering, how does the full emission spectrum vary across different storm types and regions? And what do far infrared split windows actually look like? So that split window technique, how can we potentially refine it with the far IR? And then this last question here kind of goes into what I want to start working on with my PhD, which is, can we begin to incorporate the life cycle stage of the storm into our analysis? So looking at the first question, I have a pretty picture for you all, because there's one last thing from a data perspective that we're going to incorporate into our analysis, which is we wanted a trusted reference for convection in order to compare PREFIRE to something we knew and trusted. Because again, this is new data, and not only is it new data, but it is track data. So the spatial extent of it isn't always going to be super clear if you're just looking at 8 non-contiguous tracks. So we're going to use geostationary imagery. I stole this from the Sim satellite blog, which has a lot more really pretty pictures like this. So this is visuals of convection from Himawari. And we have been using geostationary satellites from the whole geostationary ring to actually help with PREFIRE geolocation, which is what I spent a pretty significant portion of the first couple months of my master's working on. So this was a really natural kind of extension of the work I had already been doing. And it was really nice to get to start incorporating that into my thesis itself. So, like I said, we're using geostationary satellites for corroboration and validation. For all of the satellites that I'll be using, we're using level 1 products, or level 1.5 if you're European, measuring radiance and brightness temperatures. And when I had access to GOES level 2 products, I also, for contextual information, incorporated cloud phase, cloud optical depth, and cloud particle size. So we're going to be using satellites from this whole ring here, which provides complete global coverage, with the exception of the poles where everything gets kind of smeared out and the angle just isn't right for correct data. So, to actually answer that question, can PREFIRE look and identify convection successfully? I'm going to this is a twofold slide. This is an introduction to why I had to follow the process I had to follow, and also to introduce you to what my imagery is actually going to look like throughout the presentation. So this background here is that GOES information that I was talking about. These are GOES brightness temperatures. This is from a storm in northern New York and southern Ontario and Quebec. So these back here are just GOES brightness temperatures, and these are PREFIRE tracks going over it. You can see that this is a descending track because I've got timestamps on it. And these are, the 8th scene is like right here. But this is where PREFIRE actually went. So I wanted to show you this as kind of an illustration of this is where PREFIRE was. But most of what you'll actually be looking at are going to be things like this, where we have those same GOES radiances overlaid with the PREFIRE overpass, also showing the PREFIRE brightness temperatures that were measured, which leads me into kind of why we need to modify a couple of things when we're looking for convection with PREFIRE. So you'll notice that PREFIRE, the colors here, look like they're representing something a little bit different than the GOES radiances, but I haven't actually added a new color bar. And that is because this is using the same color bar. So these are technically, this green is going to be the same value as this green. So PREFIRE and GOES are not completely in alignment. PREFIRE will usually read temperatures of around 10 Kelvin more than GOES is showing. And this is for a couple of reasons. One of them is just pure footprint size. Our larger footprint encompasses a lot of GOES footprints. So GOES can pick up on details that PREFIRE might not be able to pick up on or that might get washed out. So particularly in areas like this where you have a really sharp gradient, that's why you're going to start seeing PREFIRE measuring warmer temperatures. There are a couple of other details with the way that PREFIRE is recording things that you would have to ask our data people about for more information on that. But suffice it to say that PREFIRE is generally recording about 10 degrees Kelvin above what GOES would be showing. So, that being said, I first wanted to do a sanity check and say, can PREFIRE actually pick up on convection where you would expect PREFIRE to pick up on convection or low brightness temperatures? What's the lowest that PREFIRE can actually measure realistically when I'm setting how am I going to detect convection? And so the first thing I did was just say, okay, give me all of the minimum brightness temperatures that Sat1 records in its, I refer to channel 14 a lot. This is our PREFIRE PREFIRE window channel. So this is going to be in the mid-infrared. This is in that window channel region that we're talking about. So that's what it means whenever I say channel 14 granule. So this is the minimum brightness temperatures that PREFIRE picked up in January, and the minimum brightness temperatures it picked up per granule in July. So as kind of a sanity check, I think this works pretty well. It's showing that you see really cold temperatures where you would expect the hotspots of convection to be, like over southern Africa, or over the Congo, or over Brazil. So that kind of all checks out. That makes sense to me. And the other thing I wanted to use this plot for so I wanted to use it as a sanity check, but I also wanted to use it to say, okay, if I'm looking in, say, this region for convection in January, as opposed to if I'm looking in this region for convection in January, I might want to adjust the actual thresholds I'm using in order to compensate for that regional difference. So when I say thresholds, what I mean is that I wanted to use kind of a methodology that geostationary data was already using in terms of brightness temperature thresholds for convection. So in general, brightness temperature thresholds, so saying I want all of the points in this region that are below a certain temperature, and if there are enough of these points, or we have identified a region of points below this temperature, then we can safely say this is a convective region. I wanted to use that same principle, but adjusted for PREFIRE. So I looked first at the general literature on just identifying these thresholds and found that we generally see these thresholds that are used for identifying convection range from 208 Kelvin for hot towers to 235 Kelvin to identify those larger storms. And I don't have references on here, and I should, but this I stole from Juliet Paluski's work on the same topic, and this is from, I think, a paper written in 2013 by someone named Mafon. So that being said, I said, okay, these are the GOES brightness temperature thresholds. How can I adjust this for PREFIRE? And so I mentioned Juliet's paper because I was looking broadly at her kind of definition of these because she's trying to identify from convective cores hot towers. So I looked at what she was trying to clip out with her thresholds, and I said, I'm going to try to replicate this a little bit with PREFIRE data. And so these are all of the brightness temperatures recorded by SAT1. So the previous slide was the minimum brightness temperatures, and this is all of the brightness temperatures that we record in the first week of January and the first week of July. So you'll notice, again, we see that kind of seasonal variation. And I made this sort of analogous to all of these cores here, so these blue ones. And I applied that histogram of the minimum brightness temperatures recorded over it, just for comparison purposes. And so I came up with, partially through this and partially through a lot of trial and error, I came up with thresholds of 215 for July, January, this color is messing me up, and 225 that I have varied slightly regionally, but these are the broad starting points. And the question now becomes, can PREFIRE, does this actually work? And so, can we find convective clouds? Yes. So this was identified using a brightness temperature threshold of 215 Kelvin, concurrent with a pixel requirement, so saying I want this many pixels of whatever you've identified to be under this threshold as well, to allow PREFIRE to identify the storm. So I'm identifying cold regions and kind of confirming the presence of a system. So this is what PREFIRE saw going over. This is what GOES sees when you filter brightness temperatures below 205 and brightness temperatures below 215. And then this is what you see if you look at the visible imagery for that. So this is a really strong storm. We'll get back to that later as well. But this is one of the things that PREFIRE was able to successfully identify. So, can we?
Is that zoomed in? Are those different domains, or?
These are the same domain. Good catch. So this is initially, this is 0 to 5, this is 0 to 5, and then down here is 0 to -6.5.
So they are
Yes, this is actually what PREFIRE sees. I am not sure why I have this in here because PREFIRE granules stop and start at the equator. So this, everything below here, isn't actually in this granule.
okay.
So
Sorry.
yeah, no, that's why it's different, is because this is showing what PREFIRE actually saw, and this is lying to you a little bit. I kept it mostly for illustrative purposes. So that being said, PREFIRE can, in fact, successfully identify convective cases in multiple regions of the globe using brightness temperature thresholds that are adjusted for its resolution, for the location of the investigation, and for the desired size of the storm. So now we want to ask, we've identified these storms. How does the full emission spectrum that we measure from these storms using PREFIRE vary across different regions and storm areas? And what could these split windows that I mentioned earlier, what could they look like in the far infrared? So this is kind of a twofold. I'm going to fold this question into this question. So the first thing I kind of wanted to do, I've referred, this is going to be kind of a setup slide and also a baseline slide. So first off, I've referred to the far IR and the mid IR a couple of times. On the actual spectra you see, this is where they're going to be. So this is going to be far infrared 1 is always going to be after this little gap here. And that's measuring up to about 30 microns. And then this here is our mid-infrared 2. So it contains our atmospheric window. Everything from here back has been measured already. So it's also just kind of a useful sanity check as to say, does this make sense from what I know this should be observing? So this is a storm over, I believe, Nebraska in the mid-central US on the 18th of April in 2025. And I'm using this initially to just kind of get a baseline of what does a clear sky measurement look like. According to the GOES cloud mask, this is a PREFIRE. This is not a PREFIRE. This is a clear sky measurement. And there are a couple of things that I just want to point out about this really quickly. You can see here this peak in the dirty atmospheric window that I mentioned earlier, where we're not perfectly transmitting. It's not as clean as that mid-infrared window, but it is showing a pretty reasonable description of not only what it's seeing at the cloud top, but not at the cloud top, but this is it doing its best to get through water vapor and down to the surface. And you can see it does kind of an all right job. And the last thing that I wanted to kind of point out about this is you can see as we're kind of moving further into the far infrared and these wavelengths are getting longer, the signal is becoming more and more blocked by water vapor. And so the brightness temperatures that we're recording are decreasing and decreasing and decreasing as the signal is effectively coming from higher up in the atmosphere. So you're starting to lose any kind of signal below the tropopause. So we've kind of looked at all this. I did forget to mention this is just a radar image of a station from a station located near this storm. It's not the full thing. This is, I think, about this portion. And we'll get into kind of more of what that looks like later. But this is that same storm at a much more convectively active region. So this is a cross-section of the storm taken along here. I did this in Mercatus, so sorry to anyone who doesn't like looking at that. But this kind of cross-section is this line here, showing that we do have a lot of pretty big particles pretty high up. And we also see that these are really cold temperatures in the far infrared and in the mid-infrared. This is just a really cold region of the storm. So at an outset, we're kind of expecting to see larger particles here as we are nominally near convective cores. A couple of initial kind of qualitative features. All of this is going to be talking about qualitative features because the bulk of my PhD is going to be focused on trying to make quantitative information out of this. So what signals are we identifying to investigate further quantitatively? So a couple of things I wanted to point out first is this general kind of, it's either flat or it's a, is this concave or convex? A kind of a swooping arc in this shape. As we progress throughout the far IR, you'll notice pretty distinct temperature agreement between the mid-infrared window and that far infrared kind of dirty window, which is, I think, just showing that you've got really high clouds and they're going to be in agreement because there's nothing really blocking the far IR signal. Well, not nothing, but there's less blocking the far IR signal here. And so that's the initial, this is what it would look like in a really cold region near where you might expect to see larger particles. So this is a continental example of what convection would look like. And I wanted to kind of contrast that with a maritime continent look at the same thing. So this is a storm over Brazil. I'll note a sort of interesting thing about this is in the time frame I'm looking at, so when we have PREFIRE up, we switched GOES east from GOES 16 to GOES 19. So this is using GOES 16 observations, and everything else will be using GOES 19 observations, if it's in the GOES east domain. I just thought that was kind of an interesting shift that happened in the middle of my work here. So this clear sky and convection kind of spectra is showing these 4 stars here and then moving out into what is basically a big block of clear sky area in this region. and then this really kind of deep, messy storm over Brazil. And so these two here are these two down here. We have what I was calling deep convection, and we have what I think is probably more of an anvil. And you'll see that the anvil is, these are both really flat looking spectra, except for down here where we see this pretty strong dip. And so when you contrast it to this steady decrease here, which is kind of just a water vapor signal almost, we'll see in colder regions, this really flat pattern is going to show up a lot in the far infrared. And I think the one other thing I wanted to point out about the contrast between this and continental convection as we kind of think about all of that is that here you're going to see kind of a weaker window signal in a more humid environment because of the increased presence of water vapor that I think is probably going to depress the far IR signal more than it would in a continental space. So all of that being said, there were a couple of things that I saw here that I wanted to investigate further in kind of a more just kind of observational space. So we have a couple of things that we think are potentially smaller particle size signatures in the far IR and larger signatures in the far IR, and this is going to kind of also form a bulk of what I want to look at quantitatively with my research in the future. So these are spectra taken from here and here. Scene 5 is going to be this one here, so these triangles, and then scene 6 is the stars here, represented here. So that's just telling you where it is. So you'll see these are both over really cold regions, and you can see these temperatures being really, really cold. And you also see a lot of variability in the far IR. There's pretty significant changes. You'll see down here, it's a little flatter here, and then it starts to vary a lot more here. And so if you look at the cloud particle size that GOES is reporting, these are over a pretty steady region of what GOES is telling us is between 20 and 40 microns with some bobbles around maybe where 60 would be up here. And so theoretically, what we're thinking is if you look at the extinction efficiency of dependent on particle size and wavelength in the far infrared, so this is from a paper from 2003 that I'm going to reference a lot. This is from Yang et al., and they are my best friends. But so this is kind of showing that as you get further into the far IR, the extinction efficiency varies dependent on particle size, and the way that that behaves is going to vary a lot. So when particle size gets a lot bigger, you see that the extinction efficiency becomes really consistent. But at different wavelengths, you'll see these kind of bobbles around between like 10 and 100 microns, where the extinction efficiency actually is changing. And so we're thinking that when you see things like that, this pattern kind of persists throughout the far IR. I'm showing these ones because these two channels are actually on this spectra. But theoretically, I'm thinking that if you have these and you're moving throughout the far IR and you have the right particle size and you just kind of hit on it at the right point, you're going to see this variation in what the far IR is picking up or not picking up. And then we have kind of the same logic, but saying maybe these are large particle size signatures. So this is the same thing. These are different scenes. This is going to be scene 4 is here, is these triangles that are pointing this way. And then scene 8 is these circles that are right here. And you'll see, again, that really flat signature down here. You'll see kind of in the warmer regions a really smooth descent that's not really hitting these bobbles here. You'll see like slight variations, but they're not nearly as prevalent as they were where we think smaller particles may have been. And if you look at the cloud particle size, GOES is telling us that these are, in general, really large particles, or at least for this storm, these are pretty large particles, going from like 120 to 160 microns. So this is another thing, like I said, that I want to kind of investigate more on a quantitative level and see what information I can pull out of it. So given all of that, kind of saying, okay, we have these potential particle size signatures, we have this variation, how can the far infrared maybe help with mid-infrared split window weaknesses? So we're going to focus on optically thick clouds. This is, again, from my best friends, Yang et al. in 2003 who are basically saying that the brightness temperature difference between a strongly absorbing channel, strongly water vapor absorbing channel, and 25 microns is going to be sensitive to effective particle size and insensitive to optical depth. So the varying optical depth of a cloud isn't going to impact these measurements as much as it might in the mid-IR. And you'll see here, we've got effective particle size on the bottom, we've got brightness temperature in this y-axis, and these are 3 different lines of optical depth that look essentially the same, except for at very small particle sizes. So can we apply this information to kind of say, okay, maybe we can help out with some of those split window weaknesses. As a baseline, here's what this MIR split window looks like for this same storm that we were looking at. This is a really nice split window. It shows us some nice arcs, kind of congruent with this, again, kind of simulated from Young et al. So we'll see, this was kind of a sanity check, can PREFIRE pick up what this methodology is looking at? And I've overlaid this MIR split window over the GOES 19 observations. So now that we've set up, yes, PREFIRE can pick up the split window in the mid-infrared. If we create that theoretical FIR split window, what does it look like? So this is the difference between 25 microns and 28.23 microns, which is what I'm calling our strongly absorbing channel. And we can see a really super strong relationship between channel 14 brightness temperature on the bottom and brightness temperature differences on the y-axis. A really strong kind of positive relationship that if you very clumsily use brightness temperature as a proxy for effective particle size, models about what you would expect to see here. This here is a super preliminary kind of method, so it's going to need a lot of refinement and a lot better understanding of how water vapor is affecting these processes. So how that far infrared behavior is actually going to register here. But as a preliminary first step, I think it does show some promise. And then we also, just kind of for fun, said, what does a dirty split window look like, where you're splitting a super pure, like long wave window channel with a far infrared dirty window channel, and saying, what does this actually look like? And the thing I want to point out here is, one, you have this super, super strong, just like straight line. And once we pick out how the water vapor is influencing this 19 micron channel, which sounds so easy when I say it like that, we're hoping that we can take advantage here of this really large brightness temperature range. So if you were to go back to the mid-infrared slide, this range here is like 0 to 8. Whereas here, it's going from, I think that's like 2 or 3, all the way up to 35. So if we can take advantage of this difference and kind of pick coherent science out of this, those larger ranges are going to hopefully place particle size differences in a much more easy to identify separation. So broadly speaking, that's about what a split window would look like. Kind of moving towards how can we apply this in real life, I just wanted to see if you overlay this far infrared split window that is supposed to be better at picking out effective particle size with what GOES is saying for cloud particle size, what do you get? And you'll see this isn't at all a perfect alignment. These are using really similar scales. I've flipped it because generally we'd expect smaller brightness temperature differences to register as larger particles. But they're not completely in disagreement. You'll see that what PREFIRE is tentatively calling a smaller particle could also be what GOES is calling a smaller particle or a larger particle. So in answer to what could these far infrared split windows look like, they show preliminary promise towards filling mid-infrared observational gaps by increasing the range of brightness temperature differences and making steps towards increasing sensitivity to particle size in optically thick situations. So kind of one of the last things I wanted to do in terms of bombarding you with different spectra is look at that really deep storm I mentioned in the Congo. So this is over the northern Congo. This is the Meteosat observations overlaid with the PREFIRE overpass. And the really exciting thing about this storm, which I think is super, super cool, is this is a really, really deep storm. So PREFIRE, which, as I mentioned, is recording maybe 10 Kelvin above what geostationary satellites are usually recording, saw a brightness temperature of 195 Kelvin. So this is a really, really deep storm. I had to extend my GOES color bar. You can see it goes down to 174. I think these up here are representing maybe like 180 to mid 180s. So this is a super, super intense storm, and I think it's really exciting that we have such a like smack-on PREFIRE overpass of it, because it is so strong. I like this storm so much. So the first thing we're going to look at here is this southernmost northern Congo scene, scene 4. I took basically from here all the way up to here, and I stacked them all into each other to see what kinds of trends we could pick out. So in scene 4, I wanted to point out these kind of descending patterns here, as opposed where it's really warm, kind of probably up here or down here, where you're seeing window channel brightness temperatures of above 285, which you could maybe nominally consider to be a clear sky. I have not masked this at all, so I can't be sure about that. But you'll see, again, that kind of descending signature that we talked about from clear skies in the past, and you'll also see these kind of alternations. Alternations is the wrong word. I'm more looking at variability in scene 4. And that's just what that looks like at these really cold temperatures. So we're going to kind of go down in minimum brightness temperature, which I think is really exciting as we move through these scenes. So when we look at scene 6, which is these cold regions are right here in this, we see, again, these are getting really, really cold. And we see a much stronger variation pattern kind of reflected all the way through here. We see a more kind of flat pattern at the top. It's not descending as much. This isn't entirely because we're seeing warmer MIR temperatures in scene 6 versus scene 4. No, scene 4 versus scene 6, because brightness temperatures that are recording about the same here, they do actually have different signatures from here to here. These around here are what the top of this spectrum is kind of recording. And so you'll see that the shapes here are different, which is something, again, that I want to dive into in future quantitative research. And then the last one, and this is the really exciting one, is the super, super deep. This is, so PREFIRE, again, this is PREFIRE with an 11 by 30 kilometer footprint, is reading like 195. So this is really, really, really cold. Up here, we're seeing, again, that kind of descending signature we saw down here. You'll see throughout this, I forgot to point out that in the kind of mid-regions, all of these also have kind of more flat signatures. And then I think the really interesting thing down here at a super preliminary level is this arch. So as we're going through further into the far IR, so as wavelengths are getting longer, we're actually recording a pretty steady increase in brightness temperatures at these really cold locations. So again, that's going to be like right here, where PREFIRE and, I don't know why I went that close, but where PREFIRE and, not GOES, but Meteosat are recording really, really cold temperatures. And so, tentatively speaking, if these are really, really, really tall clouds, there's a possibility that this is a stratospheric signal where we're seeing the temperature start to increase and see that kind of positive lapse rate, which is so exciting to look at in the far IR. And I'm really excited to kind of dive into more and see if this more or less hunch can be confirmed with quantitative information. And I have 2 slides on what oceanic convection looks like, and I'm gonna cut one of them just for time, because I think I'm running up on like 45 minutes now. But I did want to point out this kind of arcing effect here. So these are steadily descending, but there's a really distinct kind of downward bobble in this scenes. So this lower scene is the crosses, this upper scene is the stars, and they're just kind of going across. This is, if you're wondering, this is scene 1 to scene 8 in this particular pass. But I kind of just wanted to look at this midsection here, these cold sections, and these really warm sections, because from a shape perspective, they do behave differently from a lot of the continental stuff that I was looking at. So this is a storm over this is Cabo Verde. So you can see the coast of Africa is like right here. So I wanted to quick look at that. I also have a slide on the Indian Ocean that I'm going to skip for time, but if anybody wants to see it, I can go back to it. But in answer to that overall question of how does the full emission spectrum vary across different regions and storm areas, which is really asking, like, what can PREFIRE give us useful information and how is it changing? It does demonstrate identifiable variations between clear sky spectra, warm, cool, and really cold regions across different regions, and then within storms. So, for example, core versus anvil. And we've identified what are potentially particle size signatures, but we'll need more investigation to confirm that. And so the last thing, and this is going to be kind of moving into what I want to do for my PhD research. So this is not as fleshed out, but can we begin to incorporate life cycle stage in our analysis? So in order to start incorporating life cycle stage, I had to have a basis. So I'm going to be trying to identify life cycle with just GOES radiances. Every time I say GOES, I mean geostationary. So I stole this kind of life cycle classification metric from an analysis of, I believe, African convection that was conducted in 2007, basically saying that we can identify 5 distinct regions of convection. So you have the developing stage, where it's growing vertically and approaching its minimum brightness temperature. You have the mature stage, where it's experiencing horizontal growth and it's reached that minimum brightness temperature already. So that's this region here, this 3 region, and this here is radius, and this is brightness temperature, which I accidentally cut out. And then when it reaches its maximum radius, so this peak here, is when they're going to start calling that a dissipating storm. And then the developing and the dissipation stages are split into warm and cold regions, but for my purposes, I'm going to be performing this kind of diagnostic with just these 3 stages. So, like I said, I want to just be characterizing this life cycle stage with, again, when I say GOES radiances, I mean geostationary. But we're going to be incorporating brightness temperature minimums, the size of the temperature regions, and I haven't added these in yet, but brightness temperature gradients, to kind of come up with a life cycle characterization. So this is theoretically what we're hoping something like this looks like. So you have area below 210 Kelvin, so chosen as a threshold from, again, that brightness temperature threshold literature that I referenced earlier. And then the area between 210 and 235 Kelvin, so those less cold but still kind of a signal of convection regions. So saying along this, where the area below 210 Kelvin is increasing, is what we would call developing. And when we hit a point where the area between 210 and 235 is increasing, and maybe this area below 210 starts decreasing, is where we'd start to be calling it mature. And then this arm here of dissipation is going to be just, this area is decreasing, this area has already decreased all the way. So this is just kind of looking at the radiances that we're getting from these and hoping to be able to identify them somewhat quickly and just see what that looks like. So we're testing it out on a couple of storms. This is the picture I took. This is the last time you'll see it, I promise. I just like it so much. So I saw this storm. I saw it out the window. It had some really cool lightning. I have like probably 5 minutes worth of videos of just plain noises and lightning. And this is kind of what we're calling a developing case. This here is unfortunately not exactly this here. It is one part of this really big storm complex down here. So this stretched over like almost the entire Midwest. The reason I saw this at all was because my plane's original flight path, I think, was right through here, right here. So we deviated south in order to see it. And I've never been more grateful to have a window seat in my life. So I actually have this case because I landed and I said, I wonder if PREFIRE went over it. And so I kept checking until the granules were available, and I checked RTLE, and it turned out that it gave kind of a glancing pass. So what we're going to look at here is, this is going to be an animation that I'll play for you. We'll look in this bottom region is where this is going to pop up. So if you look here, that's the PREFIRE overpass, and then this is that storm. And you can see at the end of this animation, it has become this massive blob. Like, this is a pretty intense stuff. I stopped looking at this point because after this blob here kind of meshed into the rest of the overall storm complex. So at that point, it was kind of disconnected from what PREFIRE actually saw. So this is just kind of what does that theoretical methodology actually see. So when we have that, remember I had that triangle shape. This is the PREFIRE overpass, is this yellow thing here. It's a star. But it's right here, which is like I was saying, about where we would maybe expect that, that developing region to be, where this is, as the time steps are increasing, darkest is the earliest time step, lightest up here is the last time step. It's steadily moving up this, and then kind of along, and then because I didn't plot past where it joined it, you don't have any kind of dissipating branch here at all. So while this is kind of messy, it starts to show a little bit of a proof of concept for that theory, and that's what we want to kind of incorporate in later. So just kind of the same thing for a mature case. We've looked at this case a bunch. This is what it looks like from the top. You can see these really developed kind of convective regions. This is where PREFIRE went over it, and this is the evolution of that storm. I didn't put the PREFIRE overpass, but it was about there. And so you can see it kind of developing, moving across, and dissipating away. And this is what that same kind of plot looks like for that storm. So 210 to 235, and then increasing time steps going like this. And so we can see it's right at or a little below where that maturity inflection point that we're kind of theorizing about is. So in an ideal, yes, this 100% works world, I would have had this star like maybe here, but that's okay. This is kind of a proof of concept look at it, so this is going to be something that I want to develop a lot more with a lot more information. And then this is a quick comparison of, this is a mature spectra, these stars here, and then these two are developing. I only have stars for scene 1, which is completely my bad, but scene 2 is this one, and it's going over the same cross-track extent, so these are the same different spectra, and so we're missing, obviously, entirely that really cold region that you would see in a more mature storm down here in both of these. But I wanted to point out, one, this kind of pinching effect at the end of the far infrared spectrum for the mature that we don't see as much in the developing, although it's kind of showing up here in scene 1 where we have that more intense region. And then I also wanted to point out, again, we were talking about variability in particle size signatures, and so we see these different peaked regions. It kind of comes through really well here and a couple down here where you're seeing variability as you move further into the far infrared. So that's just the differences between a mature and a developing case, which is something that I want to start picking out again as I go into this quantitatively. Sorry, I keep hitting the microphone. But can we begin to incorporate life cycle stage in our analysis? The proposed methodology for identifying life cycle stage shows preliminary promise. Like I said, it's going to need some refinement. But our next steps will also include a refinement of PREFIRE's convection seeking algorithm, which is a fancy way of saying the thing that I made, to locate developing cases and ideally dissipating cases to facilitate further spectral comparisons. So in all, what can far infrared spectra from PREFIRE actually tell us about the radiative effects of convection? Preliminarily, it can successfully identify convective cases. The FIR split window and dirty split windows are showing some promise in filling in split window observational gaps. And regional variation between far infrared spectra does exist, both across the globe and within the storms, and that can provide us with some new information about how convection behaves in the far infrared. So you probably noticed that most of that, if not all of that, was a qualitative analysis. And so the main next step that I want to take as I move further into my work is to take the tools that I developed in this analysis to apply them to a wider range of cases, partially in using a radiative transfer model developed by a team at the University of Bologna or developed in collaboration with the team at the University of Bologna to modify atmospheric variables, what profiles we're looking at, where we're looking at, kind of creating areas of study that PREFIRE might not have passed over, and go more in depth on the case studies that I have to better understand water vapor absorption and then further develop all of the techniques that I was talking about there. In future months and years, we want to incorporate OrthCare, INCUS, which hasn't gone up yet, and Forum, which like really hasn't gone up yet, in order to extend the record, improve spectral resolution, add some vertical dimension, and just develop a better understanding of all the processes that I looked at. And then, like I said in the last slide, I want to further refine the convection-seeking algorithm to identify cases beyond just mature cases, which is what it's kind of tailored to right now. So, that being said, that's the end. I just wanted to acknowledge, well, a lot of people. First of all, Tristan, who gave me a chance and has put up with a lot of the second guessing over the past year and a bit. The administrative staff, Dee, who is not here with us anymore, Pete, Christy, Caitlin, everyone else. My GAC, so Dave and Angela. Angela, again, for all of the advice and support you've given me, and for some really interesting classes. The entire Lequier group, specifically Kyle Mattingly, Tim Michaels, and Marianne, who have helped me with a lot of my code and my coding problems and been really patient when I accidentally crashed our servers. The entire PREFIRE science team, there are a lot of people, so I'm just putting everyone under this little bucket. And then everyone I've met here and everyone that I've met throughout my academic career who has just kept me grounded and provided me with a lot of laughs along the way. So these are all of my friends. This is my beautiful cat, Olive, who is really the most important part of this slide. So yeah, after that, I think any questions?
Students first.
Yeah, maybe starting with students.
It's okay if you don't have any questions.
So you have that figure with the theoretical, like the difference plot and what the difference would be for particles of different sizes. Could you pull that up?
Yeah.
I just want to make sure I'm understanding this.
Was that the one in the intro?
Yeah.
Yeah. Okay. Let me just.
Go over that.
Sorry. I probably could have scrolled. This one?
Yeah.
Yeah.
So you're saying that at the ends of that, so this is the difference between, okay, 11, 12. At the ends of that where the isolines are converging, that's where you have trouble differentiating between particle sizes using this method.
Yeah.
So is this a theoretical model, I assume?
So this here is this picture right here, this representation is generated theoretically, but the actual methodology is not just theoretical.
Yeah. Well, so my question is basically, does this theory exist but for whatever the differences you're looking for? Like, has anyone looked at those and looked at those actual plots?
Let me just. Okay, so not this.
Okay.
You had a plot.
Yes, and I've forgotten where it is. Oh, yeah.
Yeah.
Yes, this here.
Okay.
So this is actually the same group, a much different paper. Looking at pretty much everything that's been done here is done on a theoretical basis because we don't have these measurements quite. So this is a they modeled a bunch of different size distributions, different atmospheric conditions across, and modeled what the brightness temperature measurements would be from, I want to say the range of this paper was 10 to 100 microns. So from that mid-infrared region all the way out, like way further into the far IR than we have. And so the basis for performing this one here was that kind of theoretical, this image here.
Okay. I guess so go back to the previous slide.
Is the previous slide
The one with in the mid-infrared, those bands. Sorry.
That's okay.
So those are the same plots, but in the far infrared, those lines are all very tightly constrained to each other.
Yeah.
Okay. And so, okay. So you wouldn't be able to do much about the effective particle size is still very different over those, but your optical depth stays about the same. So you wouldn't be able to tell where in the cloud it is. You can only tell what the particle size is.
This information is purely about particle size.
Okay. Okay. Thank you.
Mhm.
I was a little confused by that, and I appreciate clarification.
Yeah.
If there's more students, let them go first.
There's a. I saw you about the same time. I guess Larissa and then Tim.
Yeah, interesting presentation. I'm curious, like, you kind of motivated this by saying you care about Earth's radiation budget, and I guess specifically, I assume like high cloud effects on the radiation budget. And I'm just wondering kind of what and this is probably beyond your PhD, but like what the path towards improving our understanding of those looks like from this work.
Yeah. So, can
Maybe
I?
that's more a question for Tristan, but
I can go back. So it's mainly this here, is the understanding that kind of radiative balance. When I say never measured globally, that means that our understanding of the radiative balance coming from long-wave radiation is missing all of the information that you get from this. So it's missing the information about how convective processes are emitting in the far infrared. It's missing the information about Arctic processes, so all of those kind of polar regions that kind of motivated the PREFIRE project in the first place. All of those contributions to all-sky OLR variation are not well resolved right now. We don't understand them that well. Well, okay, we understand them,
path
but
towards understanding them.
adding
look like
this, so I don't know why I'm clicking around. So adding information about how convection is impacting that allows us to better quantify how radiation is being contributed to from the far infrared. So how
But
changes.
so far, like in this talk, you're only like comparing stuff we already know to what PREFIRE is observing, right? That's kind of the heart of what this talk was, right? So how do we add new knowledge, right? That's what kind of
Yeah.
I'm trying, like what does that look like? Like,
So-
how do we know?
When I talked about kind of moving into quantifying a lot of this information and adding that into how the far infrared can enhance the information we already have, the quantification should provide more information. So adding information that can be added to, say, global models about the radiative impacts of these processes. So basically changing how we understand how variations in these processes are going to affect different parts of the radiative budget. So adding that quantifiable information is how this should contribute. So this comparison was basically saying, is there usable information in the far infrared from PREFIRE? Like, is it worth trying to perform these distinctions?
Yeah, I mean, it seems like if really like 50% of the radiative budget isn't nailed down, then that could be like a huge impact on like cloud radiative effects. I just didn't quite follow how that's gonna be nailed down, I guess that is
Yeah,
what.
if you go back to your slide with the four things, the four boxes, yeah, that's it, right? So it's basically how do changes in height, habit, particle size, and optical depth affect that far infrared part, the bit that's missing.
Mm-hmm.
Currently, we model it, but we haven't actually observed it.
Yeah.
Okay,
So we're trying to
so it gives us
quantify
relationships.
between those
Yeah.
four things and a half that we're missing so far.
Mhm.
So
And
we'll
then-
be trying to quantify these things as opposed to just looking at spectra, but yeah.
And I think I saw Tim.
Yeah, I just wanted to mention that the two PREFIRE CubeSats have different orbits. They're not synchronized with each other, but they cross over the crater. One crosses over the crater at 8 a.m. and then 8 p.m. The other one roughly 3:30 a.m. and 3:30 p.m. So is that something that you think will be part of your future work?
Yes. I want to particularly take advantage of the way that allows us to capture diurnal cycles. This was done mostly with SAT-1, just because in the far infrared, I think that information is more reliable right now. But in the future, I want to take advantage of that overpass contrast to, again, give us more information about this, see how that varies throughout the day.
All right, I think we're a little bit over time, so I think we should thank Carolyn one more
Yes.
time.